Okay, students, let's look at some natural logarithms. We're going to be in section 7.2, the natural logarithm, which some people call the ln of x. Sometimes I call it the ln of x, and sometimes I just call it the natural logarithm. But this is how you write it, ln. So just a review of some old stuff that you really should know from college algebra, just to warm you up a little bit on it, because I'm sure it's been a while, is let's take a look at what we called exponential functions. Okay, something we called exponential functions. Well, an example of an exponential function would be something like y equaling 2 to the x, where x is the exponent. That's where it becomes something new and different. Now, if I wanted to graph this, the way we would graph it was we would always pick three particular x values, which were -1, 0, and 1. 2 to the -1 power is 1/2, 2 to the power of 0 is 1, and 2 to the power of 1 is 2. So if you graph this, you're going through the point -1, 1/2, 0, 1, and 1, 2. It looks like this. It's an always increasing function growing exponentially, and it has a horizontal asymptote, which is the x-axis. So the equation of the horizontal asymptote is y equaling 0, which again is the name of the x-axis. Okay, so that's your most basic exponential function. So what this evolves into is the exponential function e to the x, where e is approximately 2.72, so it's very close to 2. So if you come in here and you create those same table of values using the x values of -1, 0, and 1, you get 1 over e, which is like 1 over 2.72. 1 and e are just 2.72. So if you graphed it, it would be just a little bit under the graph on the left. It would stay the same y-intercept and a little bit above it on the right. So in general, they're just almost the same. Okay, they're almost the same. So your graph of y equaling e to the x is very, very similar to 2 to the x. Now the reason e to the x becomes so important is because the inverse of this function is going to be the natural logarithm. Now the natural logarithm has an assumed base of e. We don't normally write it. We just usually write the natural log of x, but there's an e is always assumed as the base. So if this is the inverse function, then we know the inverses flip their ordered pairs. So 1 over e to -1, 1 to 0, and e to -1. So if we graph this, 1 over e is like a third, which would be x value of a third down -1, the point 1, 0, and then the point like 2, almost 3, go up to a +1. Hold on, this should be a +1. This is a +1. Okay, and then its graph looks like this. All right, so this is your graph of your natural log of x. So the natural log of x does not have a horizontal asymptote. It's going to have a vertical asymptote, which is the y-axis, whose name is x equaling 0. So it has always increasing. It has a vertical asymptote instead of a horizontal asymptote, and it's the inverse of the exponential function. So we're talking about this natural logarithmic function. Notice very quickly on the natural log function, your domain is 0 to infinity, which means all x values plugged into it must be positive. So anytime you're looking at the natural log of x, remember x must be a positive value and it cannot be 0. So we're going to be talking about taking the derivative of this natural log function, and it's really a pattern that you just need to know, and it's quite easy, so don't be uncomfortable with it. That graphing and everything which I just showed you was just a reminder of what the graph of the natural log of x looked like. But the derivative is really quite simple. You just have to learn the pattern. Okay, so the derivative of the function of the natural log of x. So just to start off here, just a little bit of a review to kind of get our variables and our notation correct. If we have y equaling 3x squared plus 5x, say, plus 10, then we know that when we evaluate dy dx, that is d dx of this trinomial. and then this comes out to be just 6x plus 5. Very simple stuff. So if we're talking about the natural log of x, if we start off with y equaling, say, the natural log of u, then if I take dy dx, it's d dx of the natural log of u. Well, this is a little bit of a chain rule in that what the answer is it's 1 over u, 1 over the argument of the natural log, times the derivative of that argument. So it's 1 over the argument times the derivative of the argument. Okay, so this is really not difficult. So let's take a look at an example here. Suppose we have something like, suppose we're given, instead of just the natural log of u, we're given the natural log of 3u. So the derivative is going to be 1 over the 3u times the derivative of 3u, which is 3. So really the derivative is 3 over 3u, which oddly enough in this case happens to be 1 over u again. Alright, let's try another example. Scroll down. Again, just learning the pattern. Number 4, example 4. Suppose we have y equaling the natural log of 3x squared plus 5. Okay, the derivative is 1 over this argument, 3x squared plus 5, times the derivative of 3x squared plus 5, which is just 6x. So this becomes 6x over 3x squared plus 5. So you can see this is not difficult. We'll do another just to get very comfortable with this. Suppose we have y equaling the natural log of sine theta. Throw a trig function in this picture. Okay, the first derivative is 1 over the argument of the natural logarithm, which is sine theta, times the derivative of sine theta, which is cosine theta. So it's just cosine theta over sine theta, which we could rewrite as tangent of theta. You see these move along pretty quickly. All right, so suppose we have something like y equaling x squared times the natural log of x to the 4th power. Okay, so this is going to be 4 times x squared natural log of x to the 4 minus 1, which is 3, times the derivative of this product in these parentheses, which is going to be the product rule. So it's going to be the first, which is x squared, times the derivative of the second, which is the derivative of natural log of x, which is 1 over x, times the derivative of x, which is 1. There's the first times the derivative of the second, plus the second, which is the natural log of x, times the derivative of the first. And the derivative of x squared is 2x. Now be careful that 2x is in front of the natural log when you write this again. It's not x times 2x as the argument. It goes in front of the natural log. So this becomes what? 4 times x squared natural log of x cubed times x squared over x is x plus 2x natural log of x. That 2x again needs to be written in front of the natural log. Now you could distribute and go on with this, but I think that that's sufficient just to kind of get an understanding of what the process is. Okay, one more. Suppose we have that y equals the natural log of the natural log of x. So again, this is the argument. So the derivative is 1 over the argument times the derivative of the argument, which is 1 over x times 1. So this results in 1 over x times the natural log of x. Okay, so that's learning how to take the derivative. Now, we have some other derivatives that they're going to want us to take, and it takes a little more time to get into those, and we need the properties of the logarithm. So I'm going to close this recording and start another recording to continue through that process.